Benvenuto, everybody. Welcome to Rome, and welcome to the 25th anniversary meeting of human brain mapping. My name is Vince Calhoun, and I am the chair of the Organization for Human Brain Mapping. Rome is really an amazing place to host a meeting, and it's really quite suitable. Rome and Italy played such a major role in early medicine and neuroscience, and we're in many ways indebted to this past. I use in my slides for my fMRI course all the time a slide referring to Angelo Masso, who is an Italian who showed blood circulation varied selectively with neural activity, so sort of an early precursor to fMRI. It's also hard to believe it's been 25 years since the first Human Brain Mapping Conference in Paris. At that time, it was really just a conference, and then the second meeting in Boston, it was decided to become an organization, and you'll hear stories about that, I think, in some of the 25th year anniversary activities. And then just last year, we decided to change to a society. So really has been sort of an evolution over time. I myself started with fMRI in the early 90s. I attended the Boston meeting. I couldn't go to Paris because I was a poor graduate student, so wasn't able to afford it. But just to give you a sense of what was happening 25 years ago, the Dow had just broken 5,000 for the first time. Gas was just over $1. Michael Jordan had won 3 championships and went to do baseball, and then he had just returned to the NBA and then won 3 more championships. Windows 95 was released. JavaScript was first introduced, we're still using. The DVD was first announced. eBay had just started. Popular movies were Toy Story and Braveheart. And some of the music that was popular was Madonna and Van Halen. The Grateful Dead had just broken up that year. And the GE scanners still stored the Signa 1.5 Tesla scanners stored their data on these big optical discs. I don't know if you guys remember that at all. In many ways, I can't believe it's been that long, but it also doesn't seem like it was that long. So I'd encourage you to look at some of the blogs and some of the activities about what has evolved throughout the 25 years in this particular meeting. We have a really wonderful program. I hope you would agree. Some of our keynotes are Danny Bassett, Katie Chang, Armin Rasnahan, Thomas Yeo, Tianzi Jiang, Gil Ravinovici, and Roshan Kuhls. It really takes a village to put on an annual meeting such as this. Thanks to the program committee chaired by Lucina Uden, who worked very hard to put this together. Thanks to the OHBM central office for keeping track of everything and doing so much. Thanks to you for your attendance. And to Pietro Petriani and Emilio Riccardi, quite the tenor, huh? Who are the local organizing committee chairs. And so without further ado, I will introduce Pietro, who will be talking a little bit about Rome and giving you a welcome. So.
Do your slides. Coming up. Okay. Good afternoon, everyone, and welcome to Rome. It's a real pleasure for us, for both Emiliano, who sang his joy of being here today with you, and for myself to welcome you again in Italy. As a matter of fact, this is Back to the Future. As with Time Machine, we can go back 13 years to Florence in 2006. Those of you who entered the brain imaging field a while ago, at least 13 years ago, probably were in Florence. They remember the meeting in Florence. These are some of the events that we had in Florence, okay, here in the ceremony. And now we have the pleasure and the honor, 13 years later, of being again in Italy with the 25th anniversary, and we are here. I guess if you are here, you know where we are, so I'm not going to explain how to get here, but just to show you, and I can see slide over there, that's why I'm turning your back to you, my back to you, is where we are, and we are very close to the main attraction of the city. We are in sort of a northern part, but you can walk or take the bus to go basically everywhere, including the Vatican City. This is the train station and the other attraction here in Rome. Where we are now is, this place is a concert hall, as we showed you before, Auditorium Parco della Musica. It is composed by 3 indoor halls, also called the blobs, which I think are pretty good name for a brain imaging meeting, and outdoor theaters in a park setting. Was designed by an Italian architect, pretty famous, Renzo Piano, but I would say inspired by nature, as the 3 halls also are called the turtles. Was inaugurated on December 21st, 2002, and is actually the Europe most visited music facility. We do have a poster area. This is the main question when you organize a meeting like OHBM, and each time comes up, we have a very nice poster area, which is this one. And what also we like of this place is that all the revenue that the place will make by us, by having hosted OHBM, will actually be invested in the cultural program for the auditorium next year. So as scientists, we do care that money, actually sort of circular economy, money which is generated by science also goes back to culture. And Emiliano and I, as a local organizing chair, we had a preparatory meeting last year in November in conjunction with the Italian Society for Psychophysiology and Cognitive Neuroscience in Turin, and you see many of the friends who are here today, and we tried to put together a local organizing committee which was representative of the main center in Italy. We do forgot someone, actually we did forget someone, and I apologize, but I think that the list of names are all scientists, and before being scientists are also all of them dear friends and collaborators, are representative of Italy. We did the same thing in 2006 in Florence by having people from all over Italy, because Rome is the capital of Italy, but we feel like this is Italy which really gives embracement to you all here, all Italy. And after the ceremony and the Talairach lecture, there will be the welcome receptor in the hanging gardens around the convention center, actually the auditorium. And as usual on Wednesday night, there will be the disco night, which is at Atlantico Discotheque, which is actually the other part of the city, is Eur, which is a pretty nice part of the city to visit also. So I suggest you go there a little bit in anticipation. So this is the 25th anniversary of human brain mapping, and we felt like we had to do something more than usually you do when you have the honor and the pleasure to host a meeting, so to do some special initiative. I'm very happy to say that we gathered some money from the Iris Foundation, which was founded by Mario Guazzelli, who was a professor of psychiatry and actually was my mentor. Mario Guazzelli died a few years ago, prematurely, in 2012, and is one of those researchers and scientists and clinicians in Italy who was among the first to foster brain imaging back in the 80s, actually, when brain imaging with positron emission tomography was in the early days. He was a great mentor, and I think that he was pleased to know that the foundation put money for merit awards, which will be given to young, smart, and motivated researchers, and this somehow continues his mentorship. We also had, and you have in your bag, one of these postcards, which is a celebrating postcard for the 25th anniversary, and we will be also, tomorrow and the day after, a special annulment from cancellation stamp from the Italian Ministry of Telecommunications, so there will be somebody from the postal office over there for 2 days, and you could get your postcards, these other postcards, with special cancellation stamp celebrating the 25th anniversary of OHBM. We also did some other things which we attempt to make your stay here more enjoyable, as enjoyable as possible, and also to visit Rome, and you can see here, and will be also in the program. And no food, no meeting, and especially when you come to Italy, thinking of food is something that is inevitable. When I used to live in the United States, somebody told me once, you Italians are the only one who can talk about food while you are eating. So it's actually true, but I think we'll show you that it's a good opportunity for food, and there are different places, small selling places also here at the auditorium where you can actually have a sort of local street food. Oh. And in Rome, a couple of thousand years ago, we would say something like mens sana in corpore sano, which means you have a healthy mind if your body is healthy. So healthy brain activities are those you see here, guided city walking tour, Taoist Tai Chi in the Hanging Gardens in the morning, Tuesday and Thursday, and then jogging in the wonderful places like Villa Borghese, and also you will have Parco della Musica, a guided visit to the auditorium, and again walking in one of the villas nearby, park of the villa nearby, and to Tuesday night, 6 p.m., 25th anniversary evening concert here at Chor Hall. So I couldn't expect in 2006 that we would have had the honor again to host you all here in Italy, and in particular for such a big event like the 25th anniversary. When we started in Paris, and I was old enough, unfortunately, to be already in, I am old enough to have been already at the 1995 meeting in Paris, we were really few of us. And now the community has grown to really reach the dimensions that we see here tonight, and it's my great pleasure to give you my warmest welcome to Rome and to the meeting. Thank you.
Okay. Hi, I'm Lucina Udine, program chair for this year's OHBM, but since we're in Italy, you can call me Lucina. First of all, we'd like to start by thanking Emiliano and Pietro for organizing this beautiful event in this beautiful space. It's always a collaborative effort to put on this meeting, and it requires a lot of the local organizing committee, and you could see the huge team that has come together to put this meeting on for us. So thank you so much. Slides go forward themselves?
You should hit the left button.
Okay. Okay, so I'm very happy to be here, and it's not just because the streets are named after me. This is really a wonderful city, as I'm sure most of you have already discovered, so please take advantage of the time to look at it. We have a lot of activities planned for this year that are some extra things that we wouldn't normally do. So we have a 25th anniversary symposium featuring OHBM luminaries that will take place Monday, June 10th, over the lunch break. And just out of curiosity, for how many of you is this your first OHBM meeting? Oh, wow, that's great. How many of you is it your 25th OHBM? Oh, well, we've got a couple. All right. Wonderful. Well, whether it's your first or your 25th meeting, I think we're all going to really have a good time. There's some fun things in the OHBM mobile app, including a trivia game. There's an audience response system, which we'll go over in a second. We'll have 25th anniversary music and science, the concert that we just heard about Tuesday night. Themed poster receptions every day, and I don't know what the themes are, but I'm very curious to find out. We have a 25th anniversary photo booth where if you want to see pictures of some of those old timers 25 years ago, that's where you'll go. And we have the commemorative 25th anniversary stamp, which was organized by the local organizing committee. And we have some swag. We've got t-shirts, the brain coasters, all of these things which you can purchase to remember this meeting. And of course, stay connected. There's LinkedIn, there's Facebook. LinkedIn. Well, I guess there's Twitter. There's all of these different ways where we can tell everyone about what's going on at the meeting while you're at the meeting. And here is the fun part. So this year we're trying out an audience response system, which you can get to either from your mobile app. If you want to go ahead and give it a go, you could pull out your app, or you could just enter this gmp3.cnf.io into your browser. But if you'd like to try it out, we're going to give it a go. Is everyone game? Okay. Oops. I think I'm waiting for a slide to come up. So it's basically a way for us to ask questions of the audience and poll the results and see the results in real time. Let's see. So am I going forward? So, for example, we can vote for the People's Choice Award using the mobile app, and we can all do that hopefully by Thursday, and that's the People's Choice Award for the favorite abstract at the meeting. And we also have, of course, OHB On Demand, which will give you access to the educational courses, presentations from OHBM, and that's free to us as meeting attendees. And of course, we couldn't do this without the help of our sponsors, Philips, Siemens, National Science Foundation, and the Iris Foundation. And so are we trying out the mobile app? No? Okay. I guess we're going to have to try the mobile app during the session, so look forward to that. But I'm very excited to have you all here and hope you'll all enjoy the meeting.
So, it's my pleasure to present a few awards. The first one is the Replication Award in recognition of the best published replication study of the past year. This highlights OHBM's commitment to reproducibility in neuroimaging research and is designed to help begin to reshape the incentives towards replication. And the Replication Award this year goes to Richard Dinga. He's at the Donders Institute for Brain Cognition and Behavior in the Netherlands. And he did a study of, or he attempted to replicate a study of canonical biotypes of depression. It was using a large independent data set. Unfortunately, it did not replicate. He identified some methodological issues, which is quite important because this study has been used in subsequent studies and on additional disorders since then. So I'm hoping we'll get some good replications that replicate well, but the things that don't replicate are also good because it tells us where we should not be heading in some ways. So this is really important work to kind of figure out what we can rely on and what we can't. And so without further ado, Richard. Congratulations. Did you want to say anything?
Thank you.
He lets his science speak for him, so. Okay, next we have the Education in Neuroimaging Award in recognition of outstanding contributions to education, training, learning, professional development, and outreach to the field of neuroimaging. This year's Education in Neuroimaging Award goes to Jeanette Mumford. who's at the Center for Healthy Minds, University of Wisconsin-Madison. Jeanette is an excellent teacher. She's given lots of educational lectures and courses, and has edited a popular book on fMRI. And she goes above and beyond with creative educational media as well. She has a YouTube channel with a lot of different tutorials, a Facebook page, which is widely followed. Her nomination was supported by 550 signatories. So, Jeanette, why don't you come up and receive your award?
Well, thank you very much. I'm jet lagged and emotional, but who isn't? So first, I just want to especially thank the best mentors you could ever ask for, who helped shape a lot about my career, including how I teach. So thank you, Russ Poldrack and Tom Nichols. Also, huge thanks to all the folks who've invited me to teach at their summer courses and other courses. You know, it's really helped form a lot that turned into the YouTube channel. So the UCLA NITP course was one of the first big ones. So Susan Buchheimer and Mark Cohen and Russ Poldrack, and the University of Michigan fMRI course with John Janides, and others. And especially huge thanks to all the people who watched my videos. It means a ton to me, and just all the nice things that were said. It's just great. It makes me feel so connected to the community, so it's been an amazing experience. So thank you.
Next, we have the Early Career Investigator Award. Wait for this slide to come up. Okay, in recognition of outstanding contributions made by a young investigator to the field of human brain mapping. This year's award goes to Thomas Yeo at the National University of Singapore. He's known as the Atlas guy, has developed some functional parcellation approaches. He writes the type of papers that make you tired after reading them because they're so thorough and they involve so much work that imagining doing all that work yourself just makes you exhausted, but they're very, very good. He's a super nice guy, and he's very, very much a Star Wars fan. We'll have you come up and receive your award, Thomas. Congratulations, yes. You want to say a few words?
So I have like half an hour to do this, right? Yes. It's a joke. It's a joke.
30 seconds, not 30 minutes.
Okay. No. I'd like to thank the council for selecting me for this award. I'd like to thank my PhD and postdoc supervisors, Bruce Fischel, Paulina Golan, Randy Buckner, Michael Chi. You have really shaped my path as a scientist. I'd like to thank Tom, Lucina, and Simon for nominating me for this award. I'd like to thank everyone from my lab. You're the backbone of my lab and of the lab, and I won't be here without you. And I'd like to thank all my collaborators throughout the years. Actually, I have a very long list here, but maybe I'll just spare you that. You have taught me so much, and you have been an inspiration to me. So, thank you.
Next, we have the Glass Brain Award, which is a recognition of lifetime achievement by a lead researcher using or facilitating neuroimaging to discover original and influential findings regarding the organization and function of the human brain. This year's Glass Brain Award goes to Alan Evans, who is the James McGill Professor at McGill University. Alan is very deserving of this award. He's a renowned researcher, has done tons of things. You know, he was pioneer in statistical analysis of PET, MRI, fMRI, inhomogeneity correction. He spearheaded the big brain data set. focused on large-scale computing, brain network modeling. He's got over 130,000 citations on Google Scholar. He's won many awards. He just finished a stint as OHBM chair. And one of the things I observed there was he's a lot more than his reputation shows, and there's a lot of behind-the-scenes support that he's provided to the human brain mapping and brain imaging community that just doesn't get recognized, and he's been really spearheading and doing a lot of grassroots idea development and support and various things. So without further ado, we'll have Alan come up and receive his award. You want me to hold this way? Congratulations. You want me to hold this way?
That's probably a good idea. Wow. Dear friends and colleagues, it is a humbling experience to stand before you to receive this Glass Brain Award, and one that I will forever treasure. Such recognition from one's immediate scientific peers has a special significance for any scientist, and this certainly qualifies as the culmination of my own career. It has a special resonance for me this year, with this being the 25th anniversary of the HBM meetings. I'm looking forward to the retrospective session tomorrow that will feature many of OHBM's founding scientists reminiscing about the good old days when dinosaurs roamed the earth. Dubbed Dancing Old Fogies, this should be a fun event, so don't miss it. It's hard to believe that our fledgling organization has grown into this mature organization, a society in all but name, that it has become. Remember that when we started this thing of ours in the early 90s, people were still addicted to blobs on brains. The more the merrier. And the widespread adoption of connectomics analysis was a decade away. The application of statistical mapping to anatomy was in its infancy. There was little in the way of imaging genetics, and certainly no hackathons. Although much has changed over the years, the OHBM has retained its most important characteristics: youth, creativity, and energy. Long may that continue. For myself, the OHBM has always provided a home for interdisciplinary aspirations. When I started in this business in 1979 as a pet physicist in industry, I would go to 5 or 6 meetings a year to find what I needed. With the advent of OHBM, everybody I wanted to meet was in one place. I've had the privilege to work with some giants in the field, most notably Keith Worsley, of whom I will say more tomorrow. I'm also immensely grateful to the outstanding students who have gone through my lab over the years, most notably Louis Collins, Young He, Jason Lurch, and Yasser Aturi Medina, who now are having stellar careers as independent scientists. Watching that flowering of talent is, of course, the most rewarding part of the job. I have high hopes for the new generation coming through my lab, who shall remain nameless to avoid sowing internal discord. With the merging of neuroscience and information science along with growing international integration, this is an exciting time for us. And since McGill has no mandatory retirement policy, I look forward to causing trouble for a few more years yet. Thank you all for this most deeply appreciated recognition.
Okay, and now we have the Talairach lecture. Assume there's a slide coming up. The Talairach lecture is going to be Riitta Hari, who's a professor emerita at Aalto University. Riitta is a pioneer in the use of MEG to study neuronal activity. She's led the brain research unit at the Low Temperature Laboratory in Finland since 1982. If there ever was a good place for a low temperature lab, it's Finland. She was appointed as Academician of Science in November 2010. She has more than 300 publications, has made numerous contributions to understanding the human brain and to use of MEG as an imaging technology. She's currently focused on social neuroscience, looking at interacting brains. I don't want to take up much more time, but just to mention, did you know Santa Claus's village is in Finland? So I think of this as, as appropriate because I believe Riitta has been a gift to those of us studying the brain. And I think you'll feel the same after hearing her talk about timing and how that matters for the human brain. So let's have Riitta come up.
I got this one.
Oh yeah, good. Even
Yeah,
better.
okay. Yes, okay. Thank you very much for the introduction, and I'm really honored and happy to be here. It's a great, also for the whole MEG field, that somebody is interested in these issues. Today I'm going to speak about timing matters, and let me start with quite an old photograph. It was taken on a busy street in Paris in 1838. Okay, I still have to find out if I want to show you something, so I have to do. Okay, but it's a busy street, but you see only two persons there. One is having his booth polished, and the other person is doing the job. There are no vehicles, there are no other people seen on the street. And you certainly get my point that in this picture, like in human brain imaging, we don't get the whole truth from a snapshot or from a study where time has been too much integrated. And today I'm going to speak something about time scales in human behavior and brain function. Then I'm discuss a little bit EG and MEG. We'll give some examples of perception, cognition, and social interaction. And then later I will share with you some ideas or hypotheses, maybe differences between fMRI and MEG. Everything which is alive changes all the time. It moves, and temporal regularity is everywhere. If there's no such changes, so the object of interest is dead. So it's from extraction of energy to keeping stable states, controlling growth, and communicating. Here you see an interesting picture that was already from 1934 from Adrian and Matthews, where they show first the human alpha rhythm. As you see, it's dampened in the lower trace, dampened by opening of the eyes, and then comes back when the eyes are closed. And very similar 10 Hz rhythm is seen in the eye of a water beetle. Isn't that a little bit amazing? So it seems that our alpha rhythm is not so special as we would like to think. What about these temporal behavioral timescales? First, the reaction times, they vary from, let's say, from 150, 200 milliseconds up to 700 milliseconds, depending how many choices we have. Compared with that, mood changes pretty slowly, in seconds or even more slowly. Then we have amazingly long simultaneity windows for multisensory input. For example, here, if there's a badly dubbed movie and the audio comes first or then comes after the picture, so we tolerate windows or somehow jitter up to 350 milliseconds, and still we are happy and think that everything is fine. So our moment of now is pretty long. And it's somehow surprising because, on the other hand, we can perceive very small time differences. Like in directional hearing, time differences in sounds coming to the left and right ear, which make us feel that the sound is lateralized, can be smaller than 1/10 of a millisecond. Of course, this has to be something, it has to rely on population coding because it's much shorter time than the duration of a single action potential. But having such a very sharp directional hearing then comes as a surprise probably that we have also very sluggish perception of directional hearing in some cases. Like in this case that I call hearing backwards in time, or auditory saltation, or auditory rabbit, because it's an analog to so-called cutaneous rabbit that you have probably heard about. We first present, I have to now find a way to, okay, doesn't work. So we first present 4 left ear leading clicks to the person, and you perceive them on the left. And after that, 4 right ear leading clicks. And then you hear them on the right, but only if this interstimulus interval between these clicks is longer than 200 milliseconds. If it's shorter, you perceive like these tones would be jumping from left to right, like there would be a rabbit jumping. This is the auditory saltation. And in fact, if we just present 4 tones to the left, and then you perceive them all on the left, and then you add just 1 right-sided click after that, the location, perceived locations of all the previous clicks will be changed. And we can then say that like we would be having a lag to awareness of by about 400 milliseconds, and it's even longer in some dyslexic adults whom we have studied. It's a pretty strange phenomenon. So we lag in our perceptions, but we of course also anticipate, like this goalkeeper here, so that goalkeeper has to anticipate to which direction to go, because the ball flight time is about 400 milliseconds during a penalty kick, but the goalie's reaction time is over 700 milliseconds. Otherwise, it would not work, and the better goalies go more often to the right direction than the others. So how could we then react so fast, relatively fast? Of course, we rely much on very strong priors. We already have some kind of prior information from which direction the light is coming. Then during our whole life, we are forming different types of habits. Like William James was saying that humans are bundles of habits. And so it's very difficult then to turn out these habits. And we can also rely on very sparse information from the world. Although there's a very rich world, on the basis of these 15 moving dots, we can say that there's a healthy looking person, male person, walking on the street or here. Moreover, it turns out that despite all the richness of the environment, a gist or some kind of scheme of a skin can be obtained even with a single glance, so that means from 20 to 200 milliseconds. And it's most likely based on summary statistics of peripheral retina, an area that is very much ignored in many neuroscience studies, where we often think that just the foveal vision is something important. So some people have found that already at 120 milliseconds you can spot an animal, but you don't yet know it's a dog. So in all sensory systems, we seem to have like different grades. We have such a quick and dirty pathways, and then later on we can define these percepts. And finally, for our reaction and output, we use automatized motor patterns that speed up reactions when we are playing piano or then we are typing, so the speed is very fast, can be go up to 16 hertz. That means 60 milliseconds per item. Okay, let's then ask, is the brain slow or fast? The answer is depends where you compare it with. But the units or the pieces in our time puzzle are, of course, durations of some electric phenomena and the conduction velocities in fibers. So we have action potentials which last about 1 millisecond, then we have postsynaptic potentials which last tens of milliseconds, and the duration of the postsynaptic potential depends very much on the transmitter. So now you see that the scale is up to 500 milliseconds there, and we have very fast AMPA receptors, then we have much slower NMDA, and then we also in inhibition we have two different time courses. And it's thought currently that this AMPA would mediate feed forward connections and then re-entrance, which is very important. Feedback would be slower and would be relying on these NMDA receptors. And then we have different brain rhythms that are some kind of sum of all these phenomena, mainly related to postsynaptic potentials likely. And the main rhythms are peaking at 10, 20, and 40 Hertz, but there's a continuum, of course. So different fibers. So if we look at the conduction velocity of an electric pulse in a copper wire, it's about 10 million times faster than the conduction in an action. So thinking about that, that means that our brains are really slow. So our fastest myelinated fibers, they conduct about 100 meters per second, which is just like the speed of a Formula car. And the slow unmyelinated fibers about half a meter per second, which is like kids walking slowly towards school. Now one interesting thing is that these conduction velocities can be computed directly if you know the diameter of the fiber. So for myelinated fibers, the conduction velocity, CV here, is directly proportional to the diameter of the fiber. And for unmyelinated, it's proportional to the square root of the diameter. Here's a very interesting histological section of human corpus callosum. And you can immediately see that there's a great variability in these diameters of these fibers. And they also differ between different parts of corpus callosum, but also within certain areas you have many fibers. And if you would now compute how long will it take from going from left to right hemisphere, you end up with a quite surprising result that the interhemispheric conduction times can be from 3 to 300 milliseconds about. It sounds really strange, and one can ask that how is the brain built like this? Of course, it's also good that not all impulsation goes at the same time from left to right hemisphere, because then we would form very rigid neuronal groups that would be somehow always bound together. And if we would then look at these latencies in real life, for example, in this epileptic person, and make an MEG recording, so we can find information about callosal conduction. Like this person had a primary focus in the right hemisphere and a mirror focus somehow driven by this primary focus in the other hemisphere. And these single spikes, unaveraged spikes, are systematically delayed by 20 milliseconds in the left hemisphere. And if we now take again this our rule, so we know that the distance from one side to the other is about 130 millimeters. That means that these fibers are conducting 6.5 meters per second. So they would be small myelinated fibers, diameter about 0.5 micrometers. So that's how you could somehow try to figure out what you really are measuring. So if we would like to then build up a very fast brain, or otherwise very effective brain. So it turns out that these connections or connecting fibers can be fast or dense, but not both. It's quite interesting that the recent development of electronic chips has come to the same result, so that when they build larger and larger electronic chips, so there will be thin local connectivity and then some very thick wires go then to the other parts. And quite important findings have been those by Wang and co-workers, for example, saying that callosal fibers are about the same diameter in mammals of different sizes, going from mouse to macaque, for example. But the thickest diameter tail scales with brain size. So only a minor part of these fibers somehow scale with the brain size. And these thick fibers probably are only 1% of all. And what does this mean then? It means that here we have, at the vertical axis, we have the estimated cross-brain conduction time. And then on this horizontal axis, we have these different mammals. There's a mouse, rat, cat, gorilla, humans, and the largest are whales. And if we would take all myelinated axons in the corpus callosum, so we would see that this conduction velocity increases and increases, and we can't even in this picture go up to humans or whales because that will be really long. And then, of course, we can say that, okay, it's really bad if it takes so long time to go from left to right side. But if we take just the widest axons, so it turns out that in all these mammals, the impulses can go from one hemisphere to the other in less than 5 milliseconds. So then probably these widest axons could work as time markers. And I will come later to this topic because I'm trying to claim that these time markers are producing those signals that we measure in MEG and EG, whereas fMRI might be weighted much more to the dense, thin fibers. So now a little bit EG and MEG history, just a tiny bit. So here's an early all-male panel of EEG pioneers. So it's often said that Hans Berger was the inventor of EG, but in fact he was the inventor of the human EG, because very much had already happened before him. Spontaneous activity had been recorded, evoked responses had been recorded, effect of anesthesia and even brain death had been demonstrated, but that was all in animals. And here it's nice to notice that technology and content always go hand in hand. So there was a transatlantic telecommunication cable that was put from Ireland to Newfoundland in 1865, and then the signals were sent by Morse code, and very sensitive amplifiers were needed. And then there was Thomson who developed this galvanometer. And then Richard Caton in 1875 reported first EG that was recorded with this galvanometer. And then we can say that the scientific EG started with Nobel Prize winner Lord Adrian, who I mentioned with this water beetle eye in the paper, which was in 1934. But this paper in Nature, 1944, was important for us MEG people because in a way he predicted the emergence of MEG there. He was saying, with present methods, the skull and the scalp are too much in the way, and we need some new physical method to read through them. In these days, we may look with some confidence to the physicist to produce such an instrument, for it's just the sort of thing they can do. So, and what happens? Look, the skull is transparent to magnetic fields. So we know that also from transcranial magnetic stimulation, where you can put pulses, you produce the pulses outside the head, and then they go to stimulate the brain. And here the physics is just the reverse. So electric, mainly postsynaptic currents in the brain, in the visceral walls, they generate very weak magnetic fields. These magnetic fields are recorded with ultrasensitive sensors that nowadays still mostly are low temperature squids sensors. And then solving the inverse problem, that means computing from the measured signal pattern the underlying, most likely underlying currents, tells where the activations take place, and the time courses tell when the activations occur at millisecond scale. Here I would like to point out that one important concept in thinking about these MEG signals is the dipole moment, Q, which is current times length of that current. And so if you think of a single neuron, so it could be the length of space constant of that neuron. It tells about the strength of activation or net activation. Typically it's of the order of 1 to 2 nanoamperes, that's a current, times meter per square millimeter. So it's surprising that it seems to be the same in healthy animals and in healthy humans. But what is underneath is, of course, lots of current sources and sinks, as we see here on the left. In these intralaminar recordings, there are many ups and downs, and what we record at far distance must be a net sum of these. That means that there must be quite much cancellation. We don't see everything. There are currently nice models, computational models, with which you can already start to test the cellular hypothesis and try to understand what is a cellular basis of your signals. Here, also, I would like to also mention that this lambda, this length constant, it scales with the square root of fiber diameter. That means that large neurons dominate. And on the other hand, the total signal that we measure with this kind of methods is proportional to number of synchronized elements divided by the square root of number of asynchronized elements in a certain area. And this means that even a very tiny fraction of neurons can dominate the total signal. So summa summarum out of this is that we don't see everything. We see some net activity, and we still have to work further to try to understand what it really means. So anyhow, MEG started, and here's at the upper row we see the MEG pioneer, David Cowan, and his fancy magnetically shielded room in Cambridge. David Cowan measured with induction coil magnetometers the human alpha rhythm, magnetic alpha rhythm, but at that stage he had to use the electric EG alpha as a trigger. But then Jim Zimmerman built the first squid, and then David Cowan was able to show with his squid magnetometers very nice, much more beautiful signals for alpha, eyes closed, eyes open, etc. And in Finland then also biomagnetic measurements started quite early, just by Professor Katila, but it was not so fancy place. It was a wooden sauna, but it was nice. And anyhow, and these people, they were recording magnetocardiograms from adults, but also from unborn babies in order to understand if there were some problems. And then we together then started to make MEG measurements in just like 40 years ago, a long time. So MEG pros and cons briefly. So MEG sees through the skull, and so in the opposite direction as TMS. There's no reference electrode needed, which would distort the distribution. No skin sensor interface, so these are improvements compared with EG. No neurovascular coupling, so this is good compared with fMRI. It's silent, millisecond time resolution, reasonable spatial resolution. Strengths of generator currents can be estimated. That's quite important, and even single persons and sometimes even unaveraged traces can be studied. There's very rich information for decoding because in addition to the locations, we have the fourth dimension, which is the time. And the cons, of course, is less sensitive to deep sources, which has led some people to say that, okay, you people are cortical chauvinists. It's a term by Rodolfo Linas, so we should remember not to be that kind of people. And we miss a large part of radial currents. It's expensive, not yet movable. And maybe these negative parts were that in part they caused some friction in the community some 25 years ago, and even very well-known German newspaper Die Welt wrote that Liebe gut und billig als schlecht und teuer. I agree totally with this sentence, but I was not so happy because this schlecht and teuer, that bad and expensive, was meaning MEG, and good and cheap was EG. But nowadays, I think we know that really EG and MEG are the two sides of the same coin, and they should be considered to be complementary methods. One person who worked as a really important bridge builder between different methods, especially EG and MEG, was Fernando Lopes da Silva, who sadly passed away last month. He was editor of this EG Bible with over 1,200 pages, so lots of useful information about clinical EG and also basic EG. Fernando himself, he gave very convincing evidence for the generation of the DOC algorithm already 1978, while he was showing that the polarity of the signal reverses within the cortex. So the early MEG recordings looked something like this. So you took one location, you placed a device there, then you stimulated the person maybe 100 times, then you moved it, and then after a while you got this type of pattern. It sometimes took weeks, and then on the basis of that, then you tried to figure out where were the sources, because there were some positive signals and negative signals, and then we thought, okay, on the basis of the right-hand rule, when the current goes along the thumb, so the magnetic field has to go around it. We thought, okay, there must be activity in the primary somatosensory cortex. And it's quite clear but well understandable that soon we started to dream of multi-channel devices, not to do that tens and tens of times exactly the same thing. And in the beginning, many groups tried to combine, just use two single-channel devices, like in this picture. But of course, it's more like theater. It's not any practical interest. But then you have to build really devices where you have several sensors in the same device. In our laboratory, I would like to mention this was a very important person, Professor Oliver Lounasmaa, a widely known low-temperature physicist who considered brain research as his serious hobby. So he pushed people to really build multi-channel devices. And it soon turned out that good news was that there was not crosstalk. And little by little, there were more and more sensors, and the breakthrough was when we had devices that covered the whole scalp. Of course, then also clinical applications and cognitive applications became feasible. And this is how it looked like. First with single channel devices, and then somebody is suffering really, getting these electric pulses to the both feet for weeks, and then just to suffer for science, of course. And fortunately, this instrumentation development is still continuing, because we see, for example, here's a baby whose brain is measured with the adult 306-channel MEG, and we can only record signal from one hemisphere. But fortunately, there are now also baby MEG has been built in United States, and thus it will be possible to study the changes in maturation. For example, shortening of the latencies, changes of the polarities, etc. Very important area of application. And then the other thing is that people would like to go closer to the scalp and closer to the brain also in adults. And for that purpose, there are basically two main research lines going on. Applications of optically pumped magnetometers that you don't need to freeze. I probably did not mention, but these squids, low temperature squids, are kept immersed in liquid helium. So that means that they are at 4 Kelvin, really. But here you heat this a little bit, but you can get really to the scalp. And then also high temperature squids are something which are operating at the temperature of liquid nitrogen. So with them you can also go very close to the scalp. So these are the new developments that are going on, from which we're probably hearing more soon. So remember that one measurement with somatosensory evoked fields, which took weeks. Now the same thing can be done in about 15 minutes with these whole scalp covering devices, and we can see that there's an activity at about 20 milliseconds in primary somatosensory cortex. Before 100 milliseconds, there's activity also in the second somatosensory cortices of both hemispheres and in other areas. If we would stimulate tibial nerve at the leg, so the earliest tibial nerve responses would peak 20 milliseconds later than the responses to median nerve stimulation at the hand. But we would not notice the difference, even if we would be stimulated to the foot and leg at the same time. So this 20 milliseconds is within our simultaneously window, so we can't make a difference. There are also some cases where it takes pretty long time for the stimuli to come to the brain. And for example, here in the stimulation of the skin with laser heat, we activate then the pain-related fibers, A delta fibers and C fibers. You see that A delta fibers are activated at about 160 milliseconds after stimulation, and then these C fibers about even 800 milliseconds later. If you would have stimulated foot and the C fibers, it would have taken over 2 seconds. So if we look at monkey data, so we see that there's we go from the primary areas to later areas. By the way. Okay. So we see that the receptive field size increases as the latency increases when we go like this. So this is very well known in animals, and even in fMRI studies, okay. Hasson and co-workers have said in their study in Neuroscience 2008 that similar to the known cortical hierarchy of spatial receptive fields, there is a hierarchy of progressively longer temporal receptive windows in the human brain. But of course, in monkey, we were speaking about times up to 100 milliseconds. But they used clips of videos divided in 4 seconds, 12 seconds, and 32 seconds clips, and then this was scrambled. So that means that the data were following the same path as what we see in monkeys, but extremely much longer were all these times that were considered. What about in MEG and EG? They are very sensitive to stimulus timing, so that if we change the interstimulus interval from about 0.5 to 1 second, so we see that the responses increase a lot. And here it's for proprioception, the same is for auditory stimuli, whatever. Here I have that this response strength as a function of interstimulus interval in visual areas, and we can see the green light is for early visual cortices, where this curve has a different shape, clearly different shape compared with, for example, visual area V5 or temporal lobe. And we are seeing here that the higher the processing hierarchy, the longer the lifetime, as we call this lifetime, or is the exponent in this exponential function. Also, the later the deflection, if you have an evoked response and there are several deflections, so the later is the deflection, the longer is this tau again. And from this data, we think that we can claim that different time scales are possible also in the same brain region. It's not only that these different scales would go from one area to another, but in each brain region, you can have very many temporal scales. Sorry, now this goes. Is there the way to go back? Okay. Why are the receptive fields increasing when you go along the processing hierarchy? Of course, because there are somehow integration of several of these happenings that have small receptive fields. But another thing, Mr. Chairperson, this is going to drop. This is.
Why don't you go ahead, I can hold it.
Yeah. Okay. Also, maybe that's also worth thinking and remembering what happens in our environment. For example, we are living in 24-hour cycles because we just happen to be on this planet that has that kind of cycles. But there are lots of other physical regularities that we probably should pay more attention to. And one is this one, that in nature, according to this Newton's law, time and space are very tightly interwoven. So that, for example, if there's a wind, so it will move faster the thin branches than the trunk. So we have here the temporal frequency and spatial extent. They are very tightly coupled. And somehow that also in part could explain what we're seeing in our brains. I'm not disturbed at all, so that's So predictions and anticipation. I already mentioned this this football example, and of course then in social interaction there are lots of predictions and anticipation. For example, this is not social interaction yet, but I just want to mention that if the person is making movements, okay, now I'm really bad at this. Making movements, so we see that the primary motor cortex is starting to be activated already 2 seconds before the action takes place. Depends, of course, on the speed of movement and everything like that. This is just the level of 20 Hz activity, rhythmic activity. And at the same time, we will see change in the so-called readiness field or readiness potential. And even if the person is just looking at another person doing the same action, we see that there's such an anticipatory effect in the primary motor cortex. We can also predict, or we do predict our own utterances, so that when the subject was asked to express that kind of sequence, they say, and it's one deviant in between. If we record responses to this deviant sound, while the person is uttering, there's no change, nothing which goes about the noise, but when we replay this same thing from a tape, we will see that there's a clear response then to this deviant sound. So then, like this action potential loop that is shown here, there's already when I'm uttering something, I'm sending predictions to some other parts, and then if they match with the sensory input, there will be no extra effect. Same thing, or similar thing is seen also when you are touching yourself, compared that somebody else is touching you. Then in that case, we see change of the brain response already, the suppression already starting 30 milliseconds after the touch. And here also is, I think, a nice early study where we notice that if we present very regular stimuli to the person, but omit just sounds from time to time from there, so the auditory cortex is reacting. The auditory cortex supratemporal brain, which is somehow surprisingly peripheral part, reacting so very strongly, peaking at about 200 milliseconds, which is longer than the response to real sound, but the auditory cortex is informed that something happened, something strange happened. Now, okay, all these studies, what I was now discussing, they were such studies of, as we would call, like single-person neuroscience studies, where we assume that the person whom we study is just like a spectator, just getting stimuli in, and then we record from the brain what happened. But in reality, we are often in other types of situations, like we had two-person neuroscience, where people are active interactors with each other. So that these action potential loops that I showed previously, now they form figure 8 shaped loop here, because something what the other person is doing is I have to then anticipate. And I also made a difference here between time non-sensitive interaction, because that's something that I will send an email message today, and then you will send it when you have time, and you respond to me. So that's something from neuroscience point of view could be replaced by single-person studies, which are just in a clever manner designed. But when we have this time-sensitive interaction, something else happens. Because this interaction is an emergent property of a dyad. It can't be studied in single persons. It does not exist. The interaction does not exist in single persons. It's sometimes thought that like speech communication or conversation would be something like that, that it's encoder, decoder. So I encode something, a message, and then I say it, then you hear it, and then you decode it, and then when you have understood, then you come back and send me a message. But much better metaphor would be this three-legged race. When the two persons who are having a conversation are bound together by one leg, they are somehow bound to each other, but they have a common goal. They want to understand each other or run then to be the first in the other side of the room. And for that purpose, then most likely we would need some new type of experiments, like trying to measure brain activity at the same time from two persons. So that's something we've been developing, but we are not too far in that. Why we think it's important is, for example, this behavioral study that I like a lot. It's by Noy and co-workers, 2011, where they had a mirror game. So there are two persons, and they both have a button, and they have to move the buttons in order to somehow make similar movements. So here is the situation where the blue person was the leader and the red person had to follow. And what is in vertical axis is the velocity of the movement. You see that the blue person is making very smooth track, and the red person has then some jitter over that. So there's something like a 2 to 3 hertz jitter. Sometimes the follower is somehow going over, and sometimes undershooting. But then strange thing happens when the instruction is that don't anymore consider either of you to be the leader, but imitate each other, create synchronized and interesting motions, and enjoy playing together. So what happens is that there's extremely nice, smooth way. And this is what many people report. So this is first we can say that the players entered co-leadership states. So one was leading and one was lagging, but it goes very smoothly. And this is something what people then report. It's like feeling of togetherness. And that's something what even some people who play in small musical ensembles, they say that when everything goes fine, so they have this type of feeling. So I think this makes us to think that in social interaction there's something which happens at very, very such a short time scales, and is important for our interaction. So the complex social interaction goes surprisingly effortlessly. Most cases, of course, it sometimes goes totally wrong, but still. And there was a nice title by Garrod and Pickering. They say that, why is conversation so easy? Because it's so complicated. You don't know where it's going, but still people can talk to each other and understand each other. And their answer was that it's because humans are designed for dialogue rather than monologue. So if this is true, it means that social interaction is like a default mode, and not something that it's just building up later on when we already have all the first some basic sensory systems, some basic cognitive systems, but it's a really default. And for example, turn taking, when during conversation one person is giving the floor to the other person, it's universal and fast, surprisingly fast in all languages that have been, there's been a large amount of languages studied. It's often less than 250 milliseconds. And if we then think that how long it would require for a person to plan what he or she is going to speak next time, there was paper by Levinson in Trends in Cognitive Science, where he showed that this prediction, okay, now I have to read because maybe I see it from here because I don't have the screen anymore here. So if the person would need to start this preparation of the next utterance from early beginning, it would take 600 milliseconds. And our turn takings were typically something like 250 milliseconds. So what this means is that the persons have to anticipate what other person is going to say. And whether that could be then studied with MEG or EG, some people have started to do, and there's one such an important thing that it seems that we can't just analyze, just record MEG and then start to analyze it, but it's very useful to have some extra information. For example, in this case, persons were listening for 1 hour an audiobook, and there's an upper line is just a text, now translated to words, and then there's a vocal track, and then there's a conditional word probability, which has been got from a so-called N-gram language model. So it changes according to how probable is that a certain word occurs exactly after the other maybe 4 to 6 words or in that context, and then we have MEG. First thing to mention is that acoustic features of the stimulus are affecting the brain in a different manner in different frequency bands. That's an important difference compared with fMRI, for example. So that somehow makes things more complex, but maybe also more interesting. Here we have bands from ½ second to 8 seconds, and then the times when they were really affecting most the brain activity also differ. But this is just like a control to take away, and then we can use these language models. First, on the left, we had a word probability, which is like word frequency, without context, and then on the right, we had a word probability with context. And we see that the clear brain regions that are reacting are sensitive to these word probabilities. And they somehow main effects occur either before or later or after 400 milliseconds. And then when we compare these two conditions, statistically it turns out that the word probabilities with versus without context, they mainly recruit the left hemisphere. But just telling that it's possible to also analyze that kind of like non-average MEG if we have some extra information. So we anticipate the content of speech, but still many speech perception approaches and studies, they search for unidirectional paths only. So we, like assuming that we first have acoustical analysis, then some further analysis, still some further analysis, and then some miracle occurs, and then we have the meaning. And it's quite clear, so this type of studies are also in other fields of MEG, so that when we're looking at the activation sequences, we only look them at one direction. But here it's very clear that more attention should be then put to not interactive, but just feedback connections. And here maybe it's useful to think about the great findings by Michel Areas and co-workers 3 years ago, showing that feed-forward connections are mainly mediated by gamma band signaling and the feedback more by alpha signaling. And if we then take together also the AMPA and NMDA mediated transmission, maybe something can be made. So, Mr. Chairman and then others just 4 or 5 years ago published interesting papers of fMRI papers emphasizing time. Like first in the Nancy Koppel paper. It was like beyond the connectome, the dynome. And it says from abstract that we argue that how the brain generates temporal structure is critical to the ways in which signals are routed, combined, and coordinated. And then Vince Calhoun and co-workers, they use the term chronnectome, time-varying connectivity networks, as the next frontier of fMRI data discovery. It's really interesting, and there was also recent paper in archive still showing that the number of papers where this time-varying connectivity is studied is now increasing very rapidly. So comparing fMRI and MEG timing will certainly be extremely interesting and but not quite straightforward. For example, in the beginning, people were thinking at how we combine very accurate the spatial information from fMRI and then very accurate temporal information is that we first look at the blobs in fMRI and then we use them as seeds in MEG analysis. But it just does not work because the activation areas are not identical. There's something else happening here. And I would again like to emphasize this, somehow the complexity of MEG, somehow the different frequency bands. Like, for example, we know quite well the Golland and the co-workers study where they showed first the division of brain activations to the extrinsic and intrinsic parts. And it was shown by showing to the person, same movie twice, and then looking which parts of the brain parts react in a very similar manner. And here we see the same thing in our data. It's very nice, extrinsic part in fMRI, but then MEG, depending on the frequency band, we see different results. So this is one complication, but of course, makes it more challenging and interesting. So let me now come back to that question that I mentioned earlier. I said I was speaking about these fastest conducting fibers, and now I ask, would fMRI and MEG possibly weigh differently fast and slow fibers? And so let's think that we have a situation where we can follow these both signals along maybe 5 steps in the brain. So there's some neuronal firing, then MEG or EG signal is very soon after those, almost same times as the neuronal signaling, and then we have bold, which has a longer latency due to the hemodynamic delay. So then we can make 2 predictions. So if we compare these MEG and fMRI signals at all these locations, so if so the fMRI signals, they peak later than MEG, but if that is only because of this hemodynamic lag, so these 2, so this is now the fMRI, this is MEG, there should be somehow stable difference all the time, which is the size of the hemodynamic lag. But if they would reflect the different fibers, so we would see this type of a picture. So the vertical is there, the latency. And I will show you just briefly 4 studies. The first one, nice study about quite a complex visuospatial mental imagery. And then you see relative latencies in fMRI signals on the vertical axis. And what I would only point out is somehow the time differences here between 2 areas, like dorsolateral prefrontal cortex and motor cortex. An MEG person is extremely surprised because we never see so long differences between different parts of the brain. So maybe we just missed something, or maybe there's is a question of something else. So here's another study by Fasua Lin and co-workers where they use this fast fMRI, fast bolt at 100 millisecond resolution, and they also had MEG. And in this picture, they're plotting MEG, okay, fMRI timing as a function of MEG timing. And it turns out that fMRI shows, for example, between auditory cortex and motor cortex, shows a difference of 600 milliseconds and MEG 250 milliseconds. So what this means is that in this case, this hypothesis of different fibers would be supported. We also have some data by Jim Haxby and co-workers where we look at the responses to houses and faces, either just as like a house and face images or from these double exposure pictures. And then it turned out that fMRI MEG was telling the same story, but only after 200 milliseconds. Before 200 milliseconds, the responses were different. So I would again think that maybe there's something related to the fibers that are involved. And finally, these are some data that I was somehow worried for a long time. This is the interstimulus dependence for MEG, somatosensory evoked fields, and bolt responses with identical stimuli. And we know that for MEG, with the stimulus repetition rate about 1 Hertz, you get a nice transient response, and then it changes to a steady state response, which is much smaller. So as a function of increasing stimulus repetition rate, our responses decrease very clearly. But exactly the opposite is true for bolt signal. So what could this be? So what we then did, we did not only look at the amplitudes of these MEG signals, but we plotted everything that happened during this whole experiment. Here now we're plotting 20. Okay, this goes little by little, it goes to pieces, but it's not long. So we're plotting here either the signals as such or then the source currents. And if we then integrate these, not only looking at the fMRI, not the MEG amplitudes, we will get this type of response where even for MEG as well as a function of increasing repetition rate, the responses will increase. So most likely we, in this case, then were averaging everything, also the slow fibers. So, okay, the winner hypothesis is then, in this case, if we can, is this different fibers, which would mean, okay, so that MEG and EG weight strongly the fastest conducting pathways, whereas fMRI receives its main contribution from neuronal ensembles connected via dense, slow and thin fibers. So that's something for you to discuss then in the party. So many important timing issues I had to leave out. I'm really embarrassed that we are often using as behavioral measure just a button press, because behavior is much more. It's dance, it's music, it's many things. We should at least in the future try to analyze better the bodily movements. Also the visceral rhythms and other bodily functions might be extremely important, because there we see also rhythmic events. Some of them might be nested with our brain rhythms. And I did not discuss at all the real timekeeper brain regions like cerebellum, supplementary motor cortex or Broca's region. Just to conclude, all what is alive moves, it's dynamic. Multiple nested timescales govern human perception and cognition, and there's a strong relation to environment, including other people. Perception can be accurate or sluggish, lagging, or anticipating. Quick and dirty tricks speed up our behavior, reactions. And networks, these connectivity patterns vary in time. We should definitely know more about the re-entrant connections, and we should study the whole systems at the same time. So the whole system cannot be studied part by part separately, because then the interaction does not come out. And different methods may tell the different story. And then I decided I changed the title of my talk. It's After All, the Brain is for Timing. Thank you very much.
Present your award?
Yeah, okay. Thank you very much.
Okay. How about that talk? So thank you, Riitta. Without further ado, we have a wonderful evening reception for you today. Those of you who haven't already run out for the food to avoid the long lines, it's too late. So I now officially invite you to the opening reception of the 25th Human Brain Mapping Meeting. Buenos Aires, good evening, enjoy.